Hello, my name is Orwell Hawkins, and today I'm going to talk about the use of averaging on Ladybug RF power sensors to reduce noise and get a better, more accurate measurement. First, I will explain why and how averaging works. Then I'll demonstrate averaging on a repetitive microwave pulse stream. To help explain averaging, I have created an Excel chart that depicts noise power over time. The slide plots 25 numbers between -5 and +5 that were created with Excel's RAM between function. The numbers are averaged as shown, and a trend line is included. As you can see, as the number of samples averaged increases, the result approaches the actual power level of 0. This is how RF power sensors use averaging to give you increased accuracy. And now we'll start the demonstration. The test setup consists of a Ladybug LB680A power sensor connected to an LB2A demonstration source through 26 dB of attenuation to reduce the signal level. Now I've started the application, and remember, you can just plug in a Ladybug sensor and start using it. No zeroing is required with our sensors. I'll set the frequency to 1.9 gigahertz so I'll get an accurate measurement. Then I'll set a filter on the video bandwidth to 3 megahertz. It'll still pass our signal, but it'll reduce the noise to some extent. Okay, that helps clean up the signal a little. Now I'm going to turn the source to high power. That way we'll be able to see the pulses on the display. Then I'll set the sensor to use external triggering instead of internal triggering. That way it'll be able to discriminate the trigger from noise spikes, which are actually above the signal in some cases. Next, I'm going to turn the source back down to low power, and you'll see the signal disappears down into the noise. I'm now going to go to the Averaging and Filters tab and set up our averaging to be 100 averages and manual reset. What that's going to do is that's going to begin collecting data into the averaging buffer, and when it gets to 100, it'll just continually roll new data in and old data out. However, when we click reset, it will clear the buffer and we'll get the noise back, and we'll start the averaging process all over again. And I'm going to show you that in a minute. Before I reset the averages, I'm going to change the display resolution so that we can get a better image of the signal. I'll do that in the main tab under reference level. I'll set it to 1 dB per division, and then I'll set the reference level to -40 dBm because otherwise it'll be off the screen. And there's the signal. Now I'd like to point out that we're using an LB680A, which has a -40 dBm minimum level. If we were using an LB480A, we'd be operating 20 dB lower at around 60 or 65 dBm to the noise floor. Now I've clicked Reset Averages, and you can see the signal come out of the noise. And the sensor's doing a lot of calculations for us. It's averaging the full trace against the full trace again and again and again and again 100 times so that we get a clean representation of the signal. That's how RF power sensors use averaging to give you accurate measurements. Now if you would like trace data like this and you're operating below 10 gigahertz, I recommend the LB480A. It's a -60 dBm sensor, so it'll go down much lower than we've done here. Of course, if you need higher frequencies, then the LB680A that we've used here for this demonstration is a great sensor to use. Thank you for watching this video.